Hello everyone. So today we are going to talk about conditional probabilities. Example 8. Suppose a fair coin is tossed 4 times. What is the probability that at least one head appears? So we are trying to find out at least one head, right? So using the complement method, what is this? What is the opposite of at least one head? That is no head. That's the complement method. So 1 minus no head. So you tossed coin 4 times, no head, that means all tails. So the first one is a tail, the second one is a tail, third one, fourth one, all tails. So fair coin, that means it's 1/2, this one is 1/2, this one is 1/2, this one is 1/2. So the probability is 1/2 times 1/2 times 1/2 times 1/2. So 1 minus 1/2 to the power 4, which is 1 minus 1 over 16, which is 15 over 16. That's the answer. 15 over 16. Now let's look at example 9. Example 9 is, suppose in this experiment we know that the first toss is a tail. Then what is the probability of the same event? So now we have at least one head with first toss equal to tail. We are going to use the same complement method. So no head. Now the difference. No head in the last 3 tosses. Why is that? So there are 4 coin tosses. First one is already tail, and the original set was that here at least one head. Now the complement set says no head. So the complement set means tail, tail, tail. So this one is 1/2, this one is 1/2, this one is 1/2. So 1 minus 1/2 times half times 1/2, which is 1 minus 1/2 cube, which is 1 minus 1 over 8, which is 7 over 8. That's the answer. So knowing the result of the first toss changed the probability of the event. That gives us conditional probability. Now let's do example 10. So D and E are 2 events. Probability of D is 0.83, probability of A is 0.92, probability of D intersection A is 0.78. So we know the formula we just learned. Probability of A given D is probability of A intersection D over probability of D, which is 0.78 over 0.83, which is 0.9397. Similarly, D given A is probability of D intersection A over probability of A, which is 0.78 over 0.92, which is 0.8478. So now we learn what do we mean by independence of between two events. So two events are independent if probability of E given F is same as probability of E. So applying the formula we just learned, we see that if given two events E and F, they are independent if probability of E intersection F equal to probability of E times probability of F. So let's look at example 11. Suppose a coin is biased so that the probability of head is 2/3 and probability of tail is 1/3. It is tossed 5 times. What is the probability of HTT? So probability of HTT is same as probability of H times probability of T times probability of T times probability of H times probability of T, because independence. Consecutive tosses are independent. The outcome of one toss does not depend on the previous one or the next one. That's why we can do that. Now that we can do that, probability of head is just 2/3, tail is 1/3, tail is 1/3, this is 2/3, this is 1/3. So 2/3 square times 1/3 cube. That's the answer. Now what is the probability that two heads are obtained? This is an example where there were two heads and three tails, but the position for the heads are fixed. Now what if we are looking for all these cases where we have two heads and three tails? So two heads is, now comes the counting problem. How many different ways can you have two heads and three tails in 5 coin tosses? That answer we know, 5 choose 2. 5 choose 2 different ways you can have two heads from 5 coin tosses, and for each of them you need to multiply with the figure that we just had. So 2/3 square times 1/3 cube. So this one is number of ways to get two heads in 5 tosses, and this is probability of two heads and three tails in one arrangement. So this is for one particular arrangement, and this is the number of arrangements. So you need to multiply them to get the final answer. Okay. Now we learn the definition of Bernoulli trials. So what are Bernoulli trials? Bernoulli trials are such experiments that you can define with two possible outcomes, success or failures. Like coin toss, lottery where you have win or loss, giving birth, girl or boy, or randomly generating binary bits 0 or 1. Theorem 2 is the probability of exactly k successes in n independent Bernoulli trial is n choose k times p to the power k times 1 minus p to the power n minus k. So the formula is this one. We learned how to derive this formula from the previous example. Now let's see some application for this formula. So example 12. We have a computer program generating 0 or 1 randomly, but the probabilities are not same. Probability of generating a 0 is 0.55. Probability of generating a 1 is 0.45. Assuming that they are generated independently from each other, what is the probability of these events? How does it relate to the binary Bernoulli trial? We have this experiment generating a bit string. So generating one single bit is our example. How many bits we are generating? Total 10 bits. So n equal to 10 for this problem. And we say if we generate 1, that is success. So p equal to probability of generating 1, which is 0.45, and 1 minus p is 1 minus 0.45, which is 0.55. Okay, and k will depend on the problem itself. So we have n, p, and we just need to know the value of k for each part. So let's start with the first one. All bits have the same value. So that means all ones, all 10 of them is 1, or all 10 of them are 0. So all 10 1. So 0.45 times 0.45 times 0.45 to the power 10, or plus 0.55 to the power 10. Okay. Let's do B. B is 0 0 0 0 1 0 0 0 1 0. All these bits are independent. So this one is 0 is 0.55, this is 0.55, this one is 0.45, this one is again 0.55, this is 0.45, 0.55. So the answer is, how many ones are there? There are total 2 ones. So 0.45 to the power 2 times 0.55 to the power, how many zeros are there? Total 8. So this is the answer. Next one is 2 ones and 8 zeros. Now this one was one case of 2 1 and 8 0, but there can be many different ways of getting 2 ones and 8 zeros. Exactly how many? That answer we know. That answer is, so you have 10 tosses or 10 positions, 2 of them are ones. 10 bits, 2 are 1. So 10 choose 2 different ways you can place 2 ones in those positions, times for each position you get this answer. So 0.45 squared times 0.55 to the power 8. So for this problem you used k equal to 2. So this is your value of k. So if you compare with the formula, n choose k, p to the power k, 1 minus p to the power n minus k. So if you know the value of n, k and p, you can easily solve this formula. Next is D. 5 ones and 5 zeros. Again simple. So you have 10 bits, 5 of them are ones, so 10 choose 5. The probability of 1 is 0.45 times the number of ones is 5. Probability of 0 is 0.55 times 5. So for this problem, k is the number of success or number of ones, and that is 5. Next is example 13. So a bag contains 20 balls, 10 of them are red, 10 of them are blue. 2 balls are drawn from the bag. Let A be the event that the first one is red, B be the event that the second one is red. Are these two events A and B independent? The answer depends on the case. It depends. It depends on how the balls are replaced. Okay, so for that we take the first case. Case 1 is balls are replaced. That means once you draw the first ball, you check its color and then you put it back. Okay, so in that case, what is A? A is that the first one is red, so total 10 red balls, total 20 balls, half. P of B, 10 red balls, 20 balls, half. So P of A times P of B is half times half, 1/4. What is P of A intersection B? How many red balls can you get in the first round? 10. How many can you get in the second round? 10. How many balls are there in the first round? 20. In the second round, 20, because the first ball has been put back. So this is 100 over 400, 1/4. Same. So independent. P of A intersection B is equal to P of A times P of B. They are same, 1/4. So these two are independent. Now let's check the second case. Balls are not replaced. What does that mean? That means you take out the first ball, you check its color, whatever it is, red or blue, you do not put that in the bag. So how does that make the difference? So first, P of A is same, 10 red balls, 20 balls, so it's half. P of B is where it starts to become different. So P of B is the second ball is red. Now it can be done in two different cases. First ball is red and second ball red, or first one is blue, second one is red. So these are two possible cases, and for each case we have to figure out the probability. How does that work? So the first ball is red, that means 10 different ways, and the second ball is red. Now how many, if the first ball is red, you have taken out the first ball, so now there are 9 red balls left, and this is 20 in the first round total number of balls, and you have taken out one in the second round, it's 19 left, plus, so 10 times 9 over 20 times 19, that's the answer for the first probability, plus second probability, that would be first time it's blue, so there are total 10 blue balls, and second times how many red balls are there? 10, so 10 times 10, the denominator is the same, so this is 19 over 380 plus 100 over 380, which is same as 190 over 380, is same as half. So the probability of B is half, same as before. So probability of A times probability of B is half times half equal to 1/4. Now probability of A intersection B is where it becomes different. So A intersection B means this particular case. You see, A intersection B means that the first ball is red and the second ball is red. That means this case. Probability that A happened, that means the first ball is red, and B happened, that means the second ball is red. So this is the case, and we already calculated that probability here. So we simply put it there, 10 times 9 over 20 times 19, which is 90 times 380, which is not equal to 1/4. These two numbers, P of A times P of B and P of A intersection B, not same. So not independent. Okay, so what did we learn? We learned that two events are independent depending on how we define those two events. For this problem, if the balls are replaced, then they are independent. If they are not replaced, then they are not independent. So when you do not replace the ball that you checked in the first time, if you do not put it back, then the outcome of the second event depends on the outcome of the first event. That is why they are not independent.